To derive the differential equation of wave, let us consider a string which is held by a rigid support. The string is maintained under a tension and the free end is jerked so that a wave pulse travels through the string. Let x be the distance traveled by the wave traveling with velocity v through the string, and let y be the displacement of the string at this instant of time t. The displacement of this part of the string from the mean position after t seconds is given by y is equal to a function of t minus x by v. Yes, x is the displacement and v is the velocity, so x by v also represents time. Now let us differentiate this equation partially with respect to x as well as partially with respect to t twice. So first, differentiating partially with respect to x, dou y by dou x is equal to the first derivative with respect to x. So the derivative of this term f dash t minus x by v, and we have negative 1 by v to be multiplied. So negative 1 by v times f dash t minus x by v is the first derivative with respect to x. Now differentiating once again with respect to x partially, so dou square y by dou x square is equal to the same quantity f dash, its first derivative f double dash, negative 1 by v multiplied by negative 1 by v once again makes 1 by v square. So 1 by v square f double dash t minus x by v. So we have partially differentiated this equation with respect to x twice. Now let us differentiate the same equation with respect to t. So the partial derivative dou y by dou t is equal to f dash t minus x by v. Differentiating once again with respect to t, dou square y by dou t square is equal to f double dash t minus x by v. Now we have the same f double dash t minus x by v term here also. So we will replace this term with dou square y by dou t square. So rewriting this equation again, dou square y by dou x square is equal to 1 by v square. Now instead of f double dash t minus x by v, we will substitute this value, dou square y by dou t square. Now this is the differential equation of wave in one dimension. Now let us generalize this equation. Here y is the displacement of the particle of the medium. Here the medium is the string. So the constant particles will be the particles constituting the string. In wave propagation, there will be always a meaningful variation which makes up the wave. Say displacement in such a mechanical wave. In electric field and magnetic field, the meaningful variation is brought about by the electric field vector and the magnetic field vector. In case of matter waves, it is a wave function. So we generalize with the wave function. So replacing y with xi, which is a wave function which can represent the displacement or the electric field, magnetic field, or the wave function itself in quantum mechanics, which represents the position probability. It can also be pressure in the case of pressure waves such as sound waves. So replacing y with xi, dou square xi by dou x square is equal to 1 by v square dou square xi by dou t square. This is a wave equation, generalized wave equation in one dimension. Now to obtain the wave equation in 3 dimensions, we will write the 3-dimensional equivalent with dou square xi by dou x square plus dou square xi by dou y square plus dou square xi by dou z square is equal to 1 by v square dou square xi by dou t square. Now, excluding xi, dou square by dou x square plus dou square by dou y square plus dou square by dou z square is del square, the del operator also known as D'Ambla in mathematical terms. So, del square xi is equal to 1 by v square dou square xi by dou t square. So, this represents the differential equation of wave in 3 dimensions.